This video is going to focus on the stoichiometry involving aqueous solutions. Primarily, we're going to be focusing on precipitation reactions, hence why you see the yellow lead precipitate forming when the two aqueous solutions are mixed. The next video will focus on neutralization, acid-base stoichiometry, which is what the subject was of this week's lab. When you are dealing with reactions in aqueous solution and you need to find out something about their quantities, you're typically going to have to use the molarities and volumes to help you find moles. If you have information about the volumes and molarities of both reactants, you'll need to find your limiting reactant, going back to what we did at the beginning of this unit. And then once you have that information and you know what product or what substance you're trying to find out about, find its moles and then convert to the units that you're looking for. I'm going to come back to this next slide because it looks kind of crazy and it'll be part of the very last problem. So we're going to go ahead and focus on the first one right now. But basically, when you're dealing with what ions are remaining in your solution, you'll have to look at the four ions you started with, the two cations and the two anions, and determine how much of each of those ions is left, and then account for their new volume. So this first question asks us to figure out how much of the sodium phosphate solution, 0.1 molar, would be needed to precipitate out all the lead-2 ions from 150 mils of 0.25 molar lead-2 nitrate. In order to do this, we do need to write a balanced equation. You could write a net ionic equation, or you can just go with the complete molecular. I'm going to go ahead and just show you the straightforward molecular one so that you see where all the ions went. So the two reactants are the lead-2 nitrate and the sodium phosphate. Lead and sodium switch places, so sodium nitrate and lead-2 phosphate get made. In order to balance that equation out, we had 3 leads on the product side, so we need 3 leads on the reactant side. That gives us 6 nitrates, so we need 6 nitrates on the product side. 6 sodiums are now on the product side, so we need 6 sodium ions on the reactant side. And again, the subscripts are just coming from crossing the charges. I only have information about one of my 2 reactants this time. I have a volume and a molarity of the lead-2 nitrate. I'm trying to find out the volume of the second reactant. So my limiting reactant is going to be my lead-2 nitrate. So I'm going to go ahead and determine how many moles of that lead-2 nitrate I have using its molarity and volume. I do have to convert that volume to liters. Molarity, remember, is moles over liters. And so once the liters cancel out, I've rewritten 0.250 m as 0.250 moles over liters, so you can see where the liters go. I see that I actually consumed 0.0375 moles of lead-2 nitrate. And I know that all of that was consumed, and that because there's a 1-to-1 ratio with lead and lead-2 nitrate, that's how many moles of the lead ions were used up. I also know what the relationship is between lead-2 nitrate and sodium phosphate according to my balanced equation, that I need 3 moles of lead-2 nitrate to use up 2 moles of sodium phosphate. So with that in mind, I can take the moles of the lead-2 nitrate I have and figure out exactly how many moles of sodium phosphate I would have needed to neutralize all of that lead-2 nitrate. And because it's a 3-to-2 ratio, when I get done with the math for this, I see that I would have 0.025 moles of sodium phosphate that would be necessary to consume all of the lead-2 nitrate. The question, if you go back, asks you to find the volume of the sodium phosphate. We know the moles of the sodium phosphate, and the question gives us the molarity of the sodium phosphate. So with those 2 pieces, we can find the volume. Remembering that volume is just moles over molarity when it comes to big M. And so if I cancel out my moles and I divide 0.0250 moles of sodium phosphate by its concentration, I get that I had 0.250 liters. You could leave it in those units, or you could convert it to milliliters, which would give you 250. So just to kind of review, I didn't know if I went back there and did that or not. Sorry, I couldn't remember. I figured out which reactant was limiting, my lead-2 nitrate, since I'm trying to find out about the other one. I found the moles of my lead-2 nitrate. I used those moles to find the moles of the substance I was looking for, sodium phosphate. And then because I wanted to find volume, I converted the moles into a form of volume liters using molarity. So once you figure out your limiting reactant, you can use that to find the substance you're trying to determine and then convert to the units you're looking for. So we're going to see a similar example of this in the second one, where we find the mass of the barium sulfate that is made when we mix a solution of barium chloride with a solution of iron 3 sulfate. We have volumes and concentrations of both reactants this time, so one of those most likely will be limiting. We'll have to figure that one out first in order to find the mass of the barium sulfate. Again, however, I need to write a balanced equation. I know my two reactants are the barium chloride and the iron 3 sulfate, and I know that one of the products is barium sulfate because iron 3 and barium have just switched locations. So iron has gone off with chlorine, barium has gone off with sulfate, and so when I write those formulas and write the fourth one, the iron 3 chloride, I need to balance the equations by balancing out the iron ions and then the sulfate ions, and that causes me to have to balance the barium. And then I think the chlorine takes care of itself. Since I have quantities for both reactants, again, I need to figure out which one is limiting, and I'm going to use the barium sulfate to help me do that. So I'm going to multiply the molarity times the volume in liters, and that gives me 0.01 moles of barium chloride are present initially, and then I will do the same thing for the iron 3 sulfate. So again, it's 0.01 moles. I'm going to use the moles of both of those to determine which one makes a smaller amount of barium sulfate. You can just go to moles with this, or if you feel comfortable, you can go straight to grams. It does not matter to me. Because I had 3 moles of barium chloride in my balanced equation, that's why you see the 3 in the denominator. I went ahead and went straight to grams, but again, you can stop at moles. It's not a problem. I used the molar mass of barium sulfate and the coefficient of 3 from the balanced equation. And when I did the math through, according to Sig Figs, I need to have 3 in my answer. I got that 2.33 grams of barium sulfate could be made potentially from the 0.01 moles of barium chloride. I'm going to do the same thing with the iron 3 sulfate, using the coefficient for iron 3 sulfate in the balanced equation, which is 1, and then multiplying it again by the mass of barium sulfate and its relative coefficient to relate the barium sulfate to the iron 3 sulfate. When I do that through, I get that 7 grams of barium sulfate is possible. Again, I am limited by the reactant I would run out of first, which in this case would be the barium chloride. So the amount of barium sulfate that I can make is the amount made by my limiting reactant, the barium chloride, 2.33 grams. So as a review, I looked at both reactants after I wrote my balanced equation because I had information for both of them. I used that to find the moles of both of those reactants. I then used the moles of those reactants to determine how much of the substance I was looking for, barium sulfate, I could make. I had the option to stop this at moles and then do the multiplying by the molar mass, and I think part of the reason I did this, if you look at this slide, is pretty busy, and I was just trying to get it all on one slide for you all. But if you wanted to stop at moles of barium sulfate, you could do that, and then you could use the moles of barium sulfate made by the barium chloride to get you your grams, the 2.33. Sorry I kept hitting that. So our last question is going to be similar to the one you just saw, but we're going to add a twist onto it, the ion concentrations at the end. How many grams of silver chloride can be made if you're going to combine 100 mils of 0.2 molar silver nitrate with 100 mils of 0.15 molar calcium chloride? So as always, first things first, I need to write a balanced equation between silver nitrate and calcium chloride. I know one of my products is silver chloride. The other one would be the combination of calcium and nitrate, Ca parentheses NO3 parentheses 2. Because I had 2 chlorines in calcium chloride, I would need 2 in the AgCl. That forces me to have 2 AgNO3s, which works out quite nicely with the 2 NO3s and CaNO3 too. In this problem again, I have information about both reactants, so I need to find the moles of each reactant and determine which one I'm going to run out of first. 0.02 moles of silver nitrate is present with that volume and concentration. And then I believe when you go through and do it for calcium chloride, you're going to get 0.015 moles of CaCl2 is present. At this point, I can use those moles to determine how many grams of silver chloride I can make. Again, you can stop at moles or you can do it in one step, which I think I chose to do in part because of the space issue. 2 came from the 2 in front of silver nitrate in the balanced equation. And then I'm going to put grams of silver chloride in the numerator. The molar mass of silver chloride went in front of grams along with its coefficient. Multiply and divide, and that gives me 2.9 grams of silver chloride can be made from that many moles of silver nitrate. I need to figure out which reactant is limiting, so I'm going to take the 0.015 moles of calcium chloride, look at the balanced equation and see that it's a 1:2 ratio, but I need to account for the molar mass of silver chloride, so that's why the 143.32 grams is there. The moles cancel out. When I multiply and divide, I get that 4.3 grams of silver chloride could be made from all of that calcium chloride that was present. So the amount that I actually made, again, is based on my limiting reactant, the silver nitrate. So 2.9 grams of silver chloride is all I could prepare. When I look at this equation, I see that I had 4 ions over here on the reactant side. A silver ion, a nitrate ion, a calcium ion, and a chlorine ion. I know how many moles of silver nitrate I had present, and I know how many moles of calcium chloride I had present. Because there are 2 chlorines and CaCl2, I don't actually have 0.015 moles of chlorine, I have 0.030. The calcium is in a 1:1 ratio, so that gives me its moles. The silver and nitrate are in a 1:1 ratio, so the 0.02 moles is also representative of the silver and the nitrate ions as well. My volume of my solution has doubled. It's gone from 100 to 200. And so you may remember back from the slide that I kind of skipped over initially. Those are things you kind of needed to know. You need to find the moles of each reactant, and then you need to find the volumes. And then you need to identify which ions were involved in making your precipitate, which one was used completely, which ones just were spectators, and then which one was in excess. So if we go back to the question that we were just on, sorry, I skipped ahead. If we go back to the question that we were just on, we know that silver nitrate was our limiting reactant, and because silver chloride was our precipitate, that we completely used up all of the silver to make that 2.9 grams of silver chloride. So silver is our limiting reactant ion, while chlorine is our excess reactant ion. The calcium and the nitrate are spectators, and so all that changed for them was the fact that they were diluted because of the increase in volume. So if I move on to the next slide, what I've gone ahead and done is taken the information we got from the previous one, the moles of the 2 reactants, along with the new solution volume. We already determined that silver nitrate was limiting, so because silver nitrate was limiting, the concentration of silver in this solution is now at 0 because it was completely used. For calcium and for nitrate, we have to account for how much calcium we had originally in the new volume. It's a 1:1 ratio between calcium and calcium chloride. So there's 0.015 moles of calcium ions present in a 0.2000 liter solution. So the concentration roughly halved. The same thing occurred for nitrate. There's only 1 nitrate in silver nitrate, so therefore the moles of silver nitrate are the same as the nitrate ion, and then we divide it by the new volume, so the concentration halved as well. This excess ion is the one that we've got to focus on right now. And so if I go back to the previous slide where we went through the steps, it says we need to figure out how many moles were used to combine with that limiting reactant ion. So that should be pretty similar to figuring out how much of the excess reactant remains that we did in the lab stoich questions initially. Okay, well, if we started with 0.015 moles of calcium chloride, and there are 2 chlorines in calcium chloride, we actually started with 0.03 moles of chlorine. We know that all of the silver was used, and because the silver and chlorine are in a 1-to-1 ratio, therefore we must have used 0.02 moles of the silver to completely use up, in order to use up completely all of the silver present in that mixture. So to get the moles of chlorine that remain, we take the amount we start with, the 0.015 doubled, subtract away from it the amount that was used, 0.02, and that tells me how much was left over. In order to find the concentration of the chlorine, I do that just like I did calcium and nitrate. Now that I know how much chlorine I have left over, I take the 0.01 moles, I divide it by the 0.2 liters, and that gives me a very small concentration because a lot of the chlorine was used, of 0.050 molar. I know that this step here is a little crazy. It's really important to pay attention again to what ions are spectators, what ions are completely consumed, and then what ion is in excess. And just to keep in mind with the excess one, you're doing the same thing you did when you were finding the amount of excess reactant remaining. We're just doing it specifically for an ion.